So Thursday is our last quiz. And that'll be it for the grading part of the course. So today I thought it would, I'd stand up here and answer any questions that anybody has about plant-water relations. Fire up there, Sean. You know my question. Who screws up the screen every day? You know what it is? I think somebody has a laptop that they put up. Looks different.
The same for me.
Okay, anybody have a question? You ready to take the exam today then? No questions? I wish I could give it today, but I just haven't made it up yet. No questions?
I have one question. It's more related to plants that they are standing in water,
Yeah.
and how they are showing that water stress symptoms for them. I'm more interested for that because I didn't understand that very well. Is that we need to relate that just to the dryness of the air, or there is something else there?
It's a couple of things. So the what do they call the proximate cause, the thing they're responding to is the dryness of the air, and the stomata will close. But it's exacerbated by the fact that the plant can't transport water fast enough to keep up with the amount of water that's being lost by transpiration. So the hydraulic system of the plant, the xylem vessels, can't supply that water fast enough. And here's my idea of what happens. So overnight things come into equilibrium. Then the stomata are closed. The sun comes up, the stomata open. Water starts being lost from the leaf. Right? That loss of water initially is coming from within the leaf itself. So the leaf is losing water, and its cells are shrinking because they're losing water. Now, when they lose water, their water potential changes and becomes more negative. That creates a gradient between the root system of the plant and the leaf, and water starts moving within the xylem, a difference in pressure potentials, and that moves water from below up to the leaf. If that movement of water in the xylem can't compensate for the water that's being lost to the atmosphere, then the leaf continues to lose water, and it's the total water potential and the pressure potentials of the cells in the leaf become more negative. And if that continues, and if that starts to affect the guard cells, somehow they get the idea to close, to stop that. Now, the exact mechanism how guard cells sense a dry atmosphere is not well understood, but it may have something to do with the rate of water loss from the leaf, or the rate of water loss from the guard cells themselves, through aquaporins or who knows how. But it's that combination of losing water to the dry atmosphere and the resupply of that water from the moist soil. If that gets out of balance, then the stomata will close.
good
That's how
enough.
I see it anyway. I don't know. Sure.
So the rolling of leaves, what is that?
So, like in maize and other grasses, there are certain cells in the leaf. Actually, they've got a name, I can't remember what they are, but they're really big and full of water. And when those things lose enough water, it just deforms the leaf and it rolls up like that. It's because of the anatomy and those specialized cells in the leaf that when they lose their water, things fold up or roll up. It's nothing. Yeah. You know, just like the guard cell, when they lose water, or when they gain water, they deform in such a way to open up that pore. Well, these big cells, I wish I could remember their names, but anyway, when these big cells lose water, the leaf deforms in such a way that it just rolls or folds. And that has that's useful for the plant to survive stressful condition because it, in effect, reduces the leaf area of the plant without dropping leaves, without getting rid of it. It makes the leaf area smaller so they absorb less energy. If they can't use it for photosynthesis, the plants don't want to absorb energy. That's the bad news if they can't photosynthesize with that. And so different plants have different ways of doing it. You know, legumes move from tracking the sun to avoiding the sun. Grasses and maize and other grasses roll up their leaves. Other plants do. A lot of plants move the chloroplasts within the cells so that they absorb less light under stressful conditions. And there are other so-called photoprotective mechanisms. But it's just due to the anatomy. Anybody else have a question? Sure.
During the process of cultivation and like the opening and the closing of stomatal pores, there are some water losses. I just wanted to, if you could put some light, like how much are these water losses in comparison to the water losses by evaporation to cause cooling, and like in terms of quantity, how are they different?
So I don't, the plant doesn't distinguish between that water loss for transpiration and water loss for cooling. It opens the stomata and water is lost, and by doing that, it cools off the leaf. So anytime the stomata are open, almost any time the stomata are open, you'll have transpirational water loss. And that's a big movement of water through the plant. Most of the water absorbed by the root system goes out the top for transpiration. In that process, the leaf cools off compared to what it would be if it wasn't transpiring water. The leaf would be much cooler. I don't know how much water, we can look at that water use efficiency. What was like 1 to 3 grams of CO2 per kilogram of water. So compared to how much CO2 is being taken up, there's a lot of water being lost moving through the plant. The benefit of that water loss is to keep the leaf temperatures moderate. Yeah, to keep them in a range of temperatures that they can function normally. And if that gets cut off, then the temperature increases. Bad things happen. But I don't think the plant, let's see if I were a plant, it seems like they open the stomata to gain carbon. And the water loss is just a consequence of that. Yeah. If a plant that has too high of a temperature, it won't open its stomata to evaporate water and cool off. It doesn't do that. It's only, ultimately, the stomatal conductance is so that, you know, the open stomata is so that the plant can be in contact. And then the water loss is a consequence of it. I don't know, is that one?
Yeah.
Does that help?
So, like based on that, if at a point, the difference in the temperature of the plant and the surrounding is not a lot. I mean, plant is almost at the same temperature. And, as a part of the process of transpiration, which involves the carbon going inside. So, how much would be the water loss at that certain point? Because, it is already not at a very different temperature. And would it be justified to say that the water loss at that point, when stomatal pores close and open, is unnecessary, or if there's no temperature regulation is required at that time?
Yeah, I guess you could say it was unnecessary. The conditions, though, under which that happens typically would be a small vapor pressure deficit or high humidity in the air, maybe cloudy conditions. And in that case, the leaf and the air could be about the same temperature, but there wouldn't be much water loss anyway under that kind of condition. And so I don't know that. It's just a suite of conditions that goes together, and there's not a lot of evaporation in that case anyway. So if it's necessary or unnecessary, I don't know, but that's just what happens. Yeah. And inside a plant canopy, typically the air is more humid than outside the canopy. So leaves that are further within the canopy have different conditions than leaves, say, at the top of the canopy. And so that's also, the plants modify their environment to some extent by evaporating a lot of water. They keep the canopy humidified, and so conditions more favorable to open stomata within the canopy than would otherwise be the case. Any other pressing questions? Or not pressing?
Sure, could you discuss the difference between red and blue light for plants a little more?
Yeah, sure. So there are two separate systems for sensing light that guard cells have. One, they're called red light and blue light, but really one is all light and the other one is blue light. And the one that's all light, the so-called red light response, is mediated by chlorophyll. So the chlorophyll absorbs light. The guard cells have the Z scheme of photosynthetic electron transport in their chloroplasts, and that electron transport generates the gradients across the thylakoid membrane that are necessary to synthesize ATP. That ATP then is an energy source that can be used to pump protons out of the guard cell and set up this sequence of steps that leads to stomatal opening. Namely, protons get pumped out, potassium moves in, chloride moves in, malate is synthesized probably internally from starch reserves. The osmotic potential in the guard cell gets more negative because the solutes are concentrated. That causes an imbalance between the total water potential inside and outside the cell. Water moves into the cell across the plasma membrane, increases its volume, increases its pressure potential, and deforms the cell in such a way that portal. The energy the first step, that pumping of protons out, comes from photosynthetic production of ATP photophosphorylation. That's the red light response. So plants that have guard cells that lack chlorophyll, like the genus of orchids I talked about, don't respond to red light. They don't open. But they do respond to blue light. Blue light makes them open. Now, blue light is still blue light response of guard cells and of other processes in the plant that are affected by blue light is an area of active research, and things are changing quite a bit. But the blue light response of stomata is qualitatively and quantitatively different from the red light response. We saw that with those experiments where the stomatal conductance was, stomatal conductance, this is time. You can have a red light that has the stomata open so far, and if you give a pulse of blue light, the stomata will respond over a long period of time, even after the blue light shut off. So the blue light isn't supplying the energy directly, but it's setting some process, a sequence of reactions that ultimately will cause protons to be pumped out of the guard cell, just like in the red light. But there's something different about it. The receptor, maybe it's zeaxanthin. Maybe it's something else. Zeaxanthin is a blue light receptor in the guard cell, but there are likely other pigments that are involved in the process, the details of which are not worked out. Mutants that lack this, there are mutants that of plants that don't that have stomata that don't respond to blue light, but do respond to red light. So it's different in that sense too. But the sequence of steps is exactly the same in responding to blue light or red light, namely protons get pumped out of the guard cell, solutes accumulate in the cell, the water potentials change, water moves in, pressure potential increases, and the cell deforms and opens up the pore. What else to say about it?
So most plants that have red light, that have the chlorophyll only are affected by red light.
Say that again. What?
Plants with chlorophyll are only affected by red light, they're not affected by blue light.
It's the guard cells. So, what is that? All green plants have chlorophyll, right? But it's the chlorophyll in the guard cells that's important for opening and closing the guard cell. So some plants don't have chlorophyll in their guard cells, even though they've got it in other cells in the leaf for doing photosynthesis. But they don't have that red light response because there's no chlorophyll there to do the photophosphorylation necessary to make the ATP to pump the protons out and start the whole sequence. Okay, so that sequence, that proton pumping, is the start of any, it is involved with any response that will open the stomata, like, say, in the dark, low CO2 concentration opens the stomata. How does that work? Well, the first step is protons get pumped out of the guard cells. Now, since they're in the dark, then photophosphorylation can't supply the energy. But guard cells are also loaded with mitochondria, and all of the enzymes associated with what we call respiration, glycolysis, all those biochemical things that respiration has, oxidative phosphorylation. So they can make ATP in the dark by the mitochondria and by glycolysis in the cytoplasm and stuff. That energy then can be used to pump the protons to open the stomata even if it's in the dark. So that's a general sequence of events that happens in the stomata, no matter what the initial event is that makes the stomata open. Blue light, red light, low CO2.
I have a question.
Yeah.
About modeling.
Yes.
I was wondering, like, what do you really consider to be important, like something for us to keep this?
All those detailed equations you have to memorize. No. I mean, what do I consider important? Okay. How about if I just step through the slides?
Yeah.
Maybe, as a way, otherwise I'd forget what I think is important. Let me try it that way. So, like this one. Okay, what I think is important. What do I? Okay. What I think is important is, and why I spend time on it is number one, to demonstrate that we can take what we know at the level of the guard cells in the stomata or on a leaf basis, or on a piece of a leaf basis. If we know the environmental conditions that regulate stomatal conductance there, that gives us some insight into what happens at the canopy level for canopy stomatal conductance and canopy water use. So that's the main reason that I go through this exercise, just to help us all remember, keep in mind that it's a useful exercise to put together things that we know on one scale and apply them to a different level of organization, is what John Pessiar said. I had a couple of quotes this first day of class or something about some of this stuff. I can't remember. It's like they were to the effect of, if you want to understand a system like a plant, then it's helpful to understand other levels of organization. Namely, from the plant we can study the cells and what's going on in the cells to get an idea of how the plant functions. But we can also step back in a larger context and see that plant as it exists in a canopy and gain some insight into what's happening with the plant by looking at the effects at the level of the vegetated canopy. Anyway, that's the reason I do it. But what's important? Okay. Well, here's Pendleton teeth equation. Of course, that's you know. No, I'm not going to do it now. Sometimes it's interesting, you know, what happens to this equation if this term is infinite? If this canopy conductance were infinite, what would the latent heat flux be? This is infinity, this term goes away. You know, anyway, let's not. Okay. Also, what's the limit as this goes to 0? Okay, but to deal with an equation like this, we need to have some way of scaling up the individual stomatal behavior to the canopy level. We've got to do it. And so my argument was the single most important factor is light to consider. And because light levels vary throughout the canopy and change on at a rapid rate, what influence does that have? Because you know that stomata respond to light, and they can respond fairly quickly to light. Okay, so here you can see different sun flexes. Because okay. So you asked what I thought were the important parts. So I'm going to tell you what I think are the important parts. Because this curve is nonlinear, we can't just average the light through the whole canopy. We can't take the incident radiation, divide it by the leaf area and say that's the mean illumination on every leaf in the canopy. That doesn't work because this is nonlinear. Mathematically, that doesn't work. The simplest thing we can do is to split the canopy into two classes. A sunlit class, where the response is fairly linear, and a shaded class, again, where the response is fairly linear, and deal with those two classes of these separately. How do we do that? Okay, I went into this little thing here to come up with the transmittance through the canopy. We have to consider the way light moves through the canopy. The transmittance through the canopy is a function of how much leaf area is in the canopy and the arrangement of those leaves in the canopy. So the leaf area index, the leaf angle distribution. Here it's symbolized by this K of theta, the extinction coefficient. It depends on the angle that you're looking at the canopy, or the angle the direct beam of the sun is moving through the canopy. That's this straight. So what aspects of canopy architecture are important to consider when we're scaling up from leaf to canopy level? How much leaf area in the canopy, the leaf area index, and the arrangement of that leaf area, the leaf angle distribution. Those are two factors that we have to consider. Then, okay, here's the example. The direction you look at the canopy determines how much you can see of the soil in the background. Okay, and different kinds of canopies, different leaf angle distributions, so different extinction coefficients, but nevertheless, we can use that simple equation of the transmittance of the direct beam of the sun. It depends on the arrangement of the leaves and the amount of leaves in the canopy. If we know that, if we know the transmittance for a given point of time for our canopy, we can divide the leaf area into sunlit and shaded fractions into these little equations. Okay, so I think what's important is the words that I'm using to describe the process, not the particular details of the equations. So please don't try to memorize these things or get hung up on remembering that. But if you see an equation like this, that should jog your memory. Oh yeah, that's important. Okay, once we can split the leaf area into those two classes, there are other equations that allow us to estimate the mean illumination in the sunlit class, the mean illumination in the shaded class. That depends on the sky conditions, namely how much of that radiation is coming from the direct beam of the sun, how much is coming from the diffuse sky, and you put them in here and you calculate these values. Then, once we have that done, we can go to our nonlinear light response curve for stomatal conductance. Calculate our illumination in the sun, go to this curve and read off a value for the stomatal conductance for those sunlit leaves. Read off the stomatal conductance for those shaded leaves. Multiply them by the appropriate leaf area and come up with the canopy conductance term. Canopy stomatal conductance. That's the simplest approach we can take that's realistic for scaling up. And it's amazing We can do it not just for stomatal conductance, but also for photosynthesis. So here's a canopy photosynthetic rate based on a light response curve for single leaf photosynthesis, also nonlinear. Well, we can use the same procedure and come up with canopy photosynthesis based on light only. It's amazing how well this first approximation works in many conditions. Here's an example. Irrigated maize up at Mead, we can match the eddy covariance values pretty well, just assuming light is the only thing that affects stomatal conductance or photosynthetic. So it's a useful approach. I argue that it's the simplest realistic approach we could take to apply what we know at the level of the leaf to a canopy situation and come up with, in this case, NE, the net ecosystem exchange of CO2 between the atmosphere and the canopy. Or we could scale up stomatal conductance, put it into an equation like Putnam-Monteith equation for this term, measure everything else in here, and come up with canopy transpiration rate of latent heat flow. Turns out, for various reasons, that's a little bit harder to do than the CO2 one, but that's what I think is important about the modeling stuff. Now, that wasn't the only modeling thing I talked about, right? So there was also this, the leaf energy budget. So for conservation of energy, what do we need to know about? Well, okay, here's what's important. This leaf energy balance, how much radiation is absorbed by the leaf, depends on the leaf optical properties, right? Both in the visible part of the spectrum and in the infrared wavelengths. Most of the sunlight that's coming in is in this part of the spectrum anyway. Okay? So the leaf optical properties affect how much light is being absorbed by the leaf. Once the light's absorbed, that's got to do something. And the two big uses of that energy are latent heat flux and sensible heat flux, evaporating water and heating yourself up with respect to your surroundings. And then I just went through step by step in this radiation balance equation. I think. Yeah, this radiation balance. The leaf energy budget in terms of the absorbed radiation, sensible heat flux, latent heat flux, and this thermal, the long wave radiation based on the temperature. And then